All right, so last time we spent a little while talking about how medicine existed and developed from ancient times based on whatever evidence we have available up until about the mid-Renaissance, early modern era. And here we're going to pick up from there and follow how concepts of disease changed. And we're going to come into the era of modern pathology as a result, trying to understand what causes disease and also where it's located in the human body. There we go. So the first thing that had to be done was actually classify diseases. It's difficult when you think about all the things that cause vomiting, all the things that cause fever, all the things that cause rash, and actually try to diagnose and separate one thing that causes that from another and how they manifest. So a lot of early modern work in the medieval era and the early Renaissance was devoted to just classifying and distinguishing diseases from each other. So that happened in the early medieval era, wasn't so prominent in the classical era, but then moved into the Islamic empires during the Middle Ages and then back into the European universities after the fall of Baghdad and later Constantinople. But at the time, the cause of disease was very, very vague. So it could be things like bad air, miasmas, spiritual judgment. There we go, get the clicker going. There's a very weird idea called contagion, a very loose idea that disease spread from person to person, but not exactly how or why. The idea that disease was a spiritual judgment put upon the person who had it was always prominent, still there. Humoral imbalance, we're still working in the humoral theory of how the body works, and that you have 4 humors, and when they get out of whack, the body develops illness, or at least becomes a very prime site that's prone to illness. And then diet. Diet has been regarded as one of the things that can affect human health forever, and thankfully it's one of the things we've had right the whole time. We haven't always gotten the particulars right, but the idea that diet can exacerbate problems with health or make you a little bit healthier has definitely been around for quite a while. So we left off with Andreas Vesalius, the first person to actually create what we'd think of as a modern concept of human anatomy and the ability to look at the body as it is, give good illustrations and descriptions of it, and also tell people how to go look for it to verify those results. Not just on the authority of the person who wrote the book, but actual experiments that can be replicated. It's thought that he actually did some work in pathology and looking at the diseased organs that he came across in his dissections, and that those were amongst some of the things in his notes that he burned when he got tired of his colleagues at Padua harping on him for doubting Galen, contradicting Galen, and when he ran off to become the physician to the Holy Roman Emperor, a lot of those notes, if not all of them, were lost. Now, Padua, where he taught, continued to be a site of medical education for many years thereafter, but that particular thread was dropped and not picked up by anybody there. So, when we get to early pathologists, one of the first names we have is kind of fun. Girolamo Fracastoro named syphilis, described its symptoms accurately, but he did so not in any sort of a book, like a scientific book or a journal. He did it in a poem about a shepherd named Syphilis, who was given the disease by Zeus for being, I don't know, he probably looked at one of the goddesses wrong. And so he was given syphilis, and that's where the disease comes from. But the description of the disease and its progression was actually very accurate. So for those of you who want to impress going into your residencies, it's good to publish some research material in an article somewhere, but I put the challenge to you, if you can get a really widely accepted poem out there, good job. And that was supposed to be funny. Okay. So moving a little further into actual pathology that we recognize, we have Jean Fresnel. So he started looking at how disease manifested and broke it down into different categories than had been present before. So disease had been categorized by physicians and scientists in the Islamic empires. He broke it down in a way that wouldn't really make sense to us now, but was a big step forward at the time. He broke it down into diseases affecting the upper part of the body, the lower part of the body, diseases that were systemic or localized to one particular area. And he actually looked at the difference between physiologic changes, pathologic changes, and how to treat diseases. So he started some of the earlier versions of categorizing disease that were later changed by subsequent physicians and scientists and brought us to the current state that we are now. So many anatomists at this point, following Vesalius, had started doing a lot more dissection and investigation of the human body, and invariably they came across pathologic changes. But these early pathologists, these gross pathologists, had the exact opposite problem that we have. What kind of people were these early anatomists dissecting? Anybody remember? Prisoners, executed criminals. Do executed criminals tend to be younger or older people? Tendency here. Tend to be younger. So a lot of these bodies that they were dissecting were young, relatively healthy for the time, and didn't have a great deal of pathology. Whereas in our laboratory, we have a hard time getting around some of the pathology that we see. We get to see tumors, we get to see strokes, myocardial infarcts, whereas at the time, the bodies that these people were investigating didn't have the wealth of pathology that we now see. And Marco Aurelio Severino in Italy had a great quote. He said, "The examination of a single body of one who has died of some disease of long standing is of more service to medicine than the dissection of the bodies of 10 men who have been hanged." So once again, enjoy the fact that you guys get to look at how pathology affects the body. If anything, we have the opposite problem in our anatomy lab, where many of our donors are emaciated because of their age and don't have that really well-pronounced musculoskeletal system. Gluteal lab at 1, first years, okay. Lower limb starts soon. You get to see some more muscles and appreciate exactly how on point this observation is. So the next big name we come up with is Franciscus Sylvius. And one thing he was very strongly in favor of that we'll pick up in the next slide is William Harvey's description of how the blood circulates. He saw that the Galenic description of blood being created in the liver, washing out over the body, and that's it, made no sense. What makes more sense is that blood through the arteries perfuses tissues and somehow gets back into the venous system. This is before the microscope, so capillaries had been theorized but not proven. He also had the radical idea that medical and physiologic activity were just based in chemical reactions. And his physiologic observations were based on the idea of the human body as a chemical factory, and that alkalination and acidification of the tissues could lead to disease. And he's right. That is true. And a lot of people these days are very obsessed with alkaline versus acidic content in their bodies. But if we haven't had this in physiology yet, I just want to put this up. Give you a moment to read. So acidosis and alkalosis are bad things, but our body really keeps us on point with that. Our lungs and our kidneys do that job. So he was right, but not in the sense of we have a massive need to artificially raise or lower our pH. Most of the time, our body takes care of it. So capillaries were finally discovered when the microscope became more common. And the person who's credited with figuring that out is Marcello Malpighi. This is some illustrations of him of the lungs of a frog, and he was able to see the actual connections between the arteries and the veins, and really proved that those connections that Harvey had postulated were there. And these are some of the actual illustrations that Malpighi drew. He did a lot of other stuff with the microscope, but that's probably the one that's the most important to us, is that he proved the circulation of the blood was possible, and perfusion of blood through tissues is what leads arteries and veins to and from the heart. Now, these doctors, anatomists, and other scientists, I'm calling them scientists. Technically, scientists didn't exist as a class at this time. They were natural philosophers, but I'm going to shortcut it by calling them scientists occasionally. But they were also gathering all the information they could from dissection. Dissection had become much more prominent, and it's starting to be done in hospitals. When people died, their progress from admission to death could be tracked, and then dissection or a postmortem was done to figure out what the actual cause of death was. So we were starting to get actual clinical studies in these small number of cases where we could look at where the disease was. The first book to really collect these was written by Théophile Bonnet, and it's got a great name, Sepulchridum Sive Anatomica Practica ex Cadaveribus Morbo Dentatis. Sepulchrum means cemetery, so it's the cemetery, or the study of human anatomy through disease of the cadaver. So it's got a good name. It was a really, really good idea. It was ahead of its time, but the problem was, you can see the 3 volumes of it, there was no internal organization. So you just kind of had to flip through and look around to see if you could find anything related to a case that you might be interested in or be trying to solve for your patients. The big step forward came a little while later with an incredibly influential book that was, unlike some others that we've talked about, was an instantaneous success. And that's going to be Giovanni Battista Morgagni's Seats and Causes of Disease. He did a very similar thing, but he used pretty much his entire career and put it into this book. He spent the time from being a young med student until his retirement tracking patients through their hospital, doing postmortems, writing up the results, and putting it into this book. And he had a very comprehensive description of how the patients came in and what the final result was. And even more important, he had an extensively cross-referenced index. So anyone with this book who had a patient who came in with an ulcer could flip to ulcer and look up all the cases that had that in common and get some idea about how the disease was going to progress, whether it resolved, whether it caused death. And like I said, unlike some other books, it was an immediate success. But the big thing that it did for the history of medicine is it was the first nail in the coffin of humoral theory. He showed that when you open somebody up, you don't find that they have too much black bile. You don't find too little blood. You find a diseased organ. He located the disease in its effects on specific organs, and that's what caused death. He wrote the first true description of appendicitis. Someone who came in after suffering for many days, bent over, unable to extend his thigh, and found that that tiny little organ in the abdomen had exploded and spread purulent material all over his peritoneum. So that's the sort of thing that he was able to show, that diseases could be localized to organs. Now, one thing that happened around this time, about 100 years later, but around this time, was the French Revolution. Now, the French Revolution was really interesting in history because it caused a tremendous amount of upheaval and a lot of backsliding in many ways. But it was really influential in development of French science. The French Revolution took all those who were in power, pretty much from the king on down, and replaced them with younger, more progressive people. Now, that was done incredibly violently in some occasions, but it meant that the older versions of things were completely open for questioning. It was encouraged that people would reject authority and start looking at things anew and trying to find new ways of describing things. And that was true in medicine as well as every other thing during the French Revolution. And even when the monarchy was reestablished, that progression and that advance in medical investigation stuck. Now, one quick thing, obviously the French Revolution was not something we want to say was an unqualified success. A lot of bad things happened, including Lavoisier had his head cut off by the guillotine. I think the comment that someone made was, what took 1 second for the guillotine to cut off cannot be done again in 100 years to grow another head like that. So just FYI, a lot of things in history are not good or bad. There's good and bad effects that can come in unexpected ways. So in France, the type of pathology that started to be studied was based around Morgagni's organic or organ-based setup. And so these guys, Marie-François Xavier Bichat and Jean Crouvallier, looked at the organs, but then sampled the organs, looked at them under the microscope, and looked for not only the gross, but the cellular changes that were occurring. And they found that diseases of organs could be subdivided further down into diseases of cells and even diseases of tissues that make up those organs. So you have your heart damaged due to inflammation of the pericardium, you end up with pathologic changes of the pericardium and the tissues. And here is a heart showing the effect of pericarditis. This is actually an illustration from Crouvallier's atlas, first color atlas of pathologic anatomy, and it's showing a very decent description of what that long-term pericarditis does. Causes growth and vegetative little bumps on the heart and the pericardium. And we're moving from the whole body, humoral theory, to an organ-based theory, now to a tissue-based theory. One more step down will take us to cells. But before we get there, we got to backtrack a little bit. because disease is not just internal. Sometimes we have diseases developed from within, but sometimes we can have illness attack us from the outside. Microbes, toxins, pollutants, things like that can also cause disease. And the first big event for this is going to be the cholera epidemic that was stopped in London by Dr. John Snow. Oh, whoops. Sorry, this one. Don't get him confused. That John Snow knows nothing. This one knows some good stuff. Okay. So John Snow, amongst other things, he was actually an anesthesiologist and an OB-GYN, but one other thing he did was he figured out that the cholera epidemic that was sweeping through an area of London wasn't based around bad air. It wasn't based around person-to-person contagion directly. It was based around the water supply. And the Broad Street pump that people were using in Broad Street had been contaminated. An actual sewer line nearby had broken and was basically filling the water supply of this well with used sewage. And cholera was just spreading based through that water. People would take the water, drink it, they'd get cholera, they'd use the bathroom, and then the disease keeps spreading. So the handle was taken off the pump and the epidemic subsided. It was the first real epidemiologic study showing how disease spreads and localizing it to a specific cause. And on the left, that's the actual map he drew of the area, pinpointing every house that had an infection and figuring out what the common denominator was. All right, so that's that. Now, medical practice and development had shifted to France and then away from France. And the next high status area for medical investigation and pathology was Vienna. So in Vienna, a massive hospital was built called the Allgemeines Krankenhaus with about 14,000 patients coming in annually. A huge number of people coming into the hospital, treated in various wings. And one thing that was standard in this hospital was that people were autopsied. So after disease, autopsy was done because it was clear that you could learn a lot about how disease progresses by checking how the body had changed over the time that they'd been there. But that was going to have some tragic effects due to the fact that no one understood anything about the germ theory of disease or how disease can spread through microbes. So we'll talk about that in just a second. The person who started the pathology program there is this guy, Karl Rokitansky, and really fun little bit of trivia. That's Karl Rokitansky, the namesake and inspiration for Mad Max Rokitansky. So he's named after him. George Miller, the guy who makes the Mad Max movies, is actually an MD. He's a doctor. He financed the first Mad Max movies by doing extra shifts in the ER. And there's lots of little anatomical medical trivia scattered throughout the Mad Max movies. So worth another look, just in case you want to, study but not study. So what was the bad thing that happened as a result of all these dissections in the hospital? At the Allgemeines Krankenhaus, there were two wings, one for obstetrics run by midwives, one for obstetrics run by the doctors. The mortality rate in the maternal wing run by doctors was ridiculous. It was around 30%. The wing run by midwives was around 3%. And nobody could figure out what the problem was, why one wing had this massive mortality rate and the other one didn't. But the cause was almost universally what was called puerperal fever, or childbed fever. Women would become infected with strep, it would spread, cause brain freeze, an infection in the uterus, and then spread through the body. They'd go septic and die. The theories being brought around were that one side was closer to a swamp, and that swampy air was bringing miasma in, that was causing the illness. But that wasn't the problem. The problem was all the doctors would go and do autopsies in the morning. This is long before the advent of rubber gloves or sterile procedure. And they'd autopsy all these people who had died of infectious disease. They'd go upstairs to the OB-GYN wing and proceed to go bed to bed doing pelvic exams of all the women who were in the wing. Guaranteed to spread infection, almost like a factory assembly line. So a terrible situation if you know anything about germ theory. No one knew about germ theory at this point. Contagion was the closest thing we had. But this fellow, Ignaz Semmelweis, was a Hungarian physician who was working at the Allegheny Krankenhaus, and he kind of figured out that there was something going on. That was some particle was coming from the dead bodies and infecting the women in the OB wing. And he instituted a policy of hand washing with kind of a lime bleach solution, a little bit of chlorine, and immediately the mortality rate shot down to about 3%, same as in the midwife wing. Now you'd think this would be great. You'd think everybody would be on board with this. Austria and Vienna in particular were very, very hierarchy happy. French Revolution hadn't happened there. The doctors at the upper level didn't like the hand washing initiative. It took a lot of time. The residents and doctors grumbled about it because it took a lot of time. It was unpleasant. Your hands smelled like bleach for the rest of the day. And essentially it got shut down. At this point, Semmelweis could have stuck it out and been able to push this forward if he'd been the right kind of person. But his brilliance at figuring out the problem did not translate into brilliance in conveying the issue to others. And he was one of those people who kind of, once he got resistance, he kind of doubled down for a minute, then quit and went away. So he wasn't really the person to push these reforms forward. It wasn't until the older tier of physicians and administrators had died and new people moved in that those reforms were made, because they knew that it was clear there was a difference and that Semmelweis was right, but he was just a terrible communicator. Now Semmelweis actually went, he became demented. He came down with dementia relatively early in life and had to be institutionalized. There's a story going around that he had a cut in his finger, and that actually led him to get septic and die of the disease he'd tried to prevent. It's an interesting story, didn't quite pan out. An actual forensic investigation after the fact shown pretty conclusively from his bones that he was beaten to death by orderlies at the mental hospital where he was interned. So mental health, yet another issue that's unrelated to this, but that's pretty much par for the course at the time. So a lot of time and energy spent to no great effect, a lot of needless death occurring thereafter because germ theory was not understood. So Vienna, we'll get back, there's a happy ending to that story eventually, but it took a while. But Vienna produced a great deal of scientific and medical advancement. That understanding of germ theory that wasn't there really caused a lot of trouble, but the investigative mindset they brought to a lot of other problems really paid benefits. So starting with Johann Peter Müller, who looked into cancer cells, this is when the Vienna, well, we'll call them pathologists now, started to understand that cells themselves that make up the tissues could be the basis for disease. It could be the place where disease was actually first manifesting, and then all the systemic problems that occurred thereafter were a result of that. So he looked into benign and malignant tumor cells and established that tumor cells were in fact derived from benign cells. They weren't something foreign. They were a modification of the existing cells in the body that had gone bad. So that's a great advancement. But the best thing that Müller did was he trained a whole bunch of people who did a lot of amazing things. And you're going to know some of these names. He trained Schwann. Schwann, in addition to naming Schwann cells, which you've heard about at this point, figured out that all animal tissues are made of cells. This was something that had been doubted. But he was able to establish that all human tissues, all animal tissues for that matter, were based on cells. That's because his friend Schleiden, who discovered that all plant tissues were made of cells, told him to check it out. So that's Schwann. Next up, Henle and his loop. Loop is only one of the few things Henle named. He established the nomenclature we use when we look under the microscope. So every time you're beating your head against this is squamous, this is cuboidal, this is stratified, you can thank Henle. He's the one who came up with the terms that we still use to describe microscopic appearance. And last and not least, we have Rudolph Virchow. Who's heard the name Virchow? Okay, if you haven't, you will. And I don't even know where to start. So here we go. Take a deep breath and prepare to feel incredibly insignificant. So here's Rudolph Virchow. At age 22, he studied under Müller in Vienna. At age 23, he became an assistant prosector working in the gross anatomy pathology service at the Charité Hospital in Berlin. 24, he wrote his first journal article wherein he discovered leukemia. Then he graduated from medical school. He founded a new journal specifically so that he would have a place to publish all of his new findings. No other journal could keep up, so he had to make his own. That journal is still in existence. It's called Virchow's Archive by some, but it's still there. He wrote a report on the typhus outbreak in a northern part of Germany and basically figured out that public sanitation was the root cause of this trouble. It wasn't poverty, it wasn't laziness, it wasn't some weird miasma. It was crushing poverty and poor hygiene that was leading to these outbreaks. And in the process, he became a massive supporter of hygienic reform, progressive causes. He was actually expelled from Berlin because he'd become so progressive. He started to make a lot of enemies in the Reichstag and other places there. He was actually challenged to a duel by Otto von Bismarck. More on that in a minute. And he returned to Berlin after it was clear he was just so unbelievably productive that they needed him there, and they established a chair in pathology for him just to get him back to Berlin. So, in addition to that, he's as well known in anthropology circles as he is in medical circles. He did a ton of work on anthropological measurements, the understanding of how different human ethnic groups vary from each other. He was a massive proponent of public health. Berlin's sewer system was amongst the worst in the world, or at least in Europe when he arrived. It was amongst the best by the time he'd retired because he was elected to political office and was able to push hygienic reforms through to improve the water and sanitation in the city. There we go. He was a very progressive liberal politician for the time. He was challenged to a duel by Otto von Bismarck, the guy with the spiky helmet. And he replied, there's two different stories on how he replied to the challenge. He said, yes, we can duel, but it must be with scalpels. And the other one he said was, okay, I'll take a typhus solution and inject it into one of two sausages, and then we'll each take a sausage and eat it and see who dies. Bismarck did not take him up on the offer. And he was present when Troy was discovered. So, challenge is out there. Go beat Virchow, people. Go do better than that. One other thing I want to mention, because we're doing actually pretty well on time. In anthropology, he was a very unusual voice for what we would now think of as sanity in anthropological circles at the time. He roundly rejected the idea of different ethnic groups and races being inferior to each other, and did a lot of a lot of studies on the people of Germany, because he, even then, in the late 1800s, was really sick of the anti-Semitic political groups that were out there talking a lot about German racial superiority, purity, and so forth. And he actually did a study showing that not all pure German children were blonde-haired and blue-eyed. And all the more damning from the anti-Semitic party lines, he showed that 14% of German Jewish children were blonde-haired and blue eyes. And 30 years later, when Hitler came to power, he used every opportunity he could to heap abuse on Rudolph Virchow for, trying to make it clear that German Jews and German Aryan-derived people were really not that different. So if you go through your life and make a massive enemy out of Hitler, so much so that he decides to run you down 30 years after your death, good job. Now, back to France. We have our first chemist, pure chemist, true chemist that we've talked about, and that's Louis Pasteur. Now, Louis Pasteur originally started training as a chemist, and his work was on chirality of molecules and using the microscope and looking at crystals and how you could have the D and L forms, and you could actually see two different forms of that crystal as time goes by. That work was important and was probably noteworthy in and of itself. But what's more important is how good he was at using the microscope and how much he was able to use it as an investigative tool thereafter. Now, we're going to talk more about him when we talk about treating disease during the next talk, but he was able to really figure out something that no one else had. The French wine and silk industries had major problems. There was a lot of contamination, and instead of having wine that went through the normal process of fermentation, it came out very, very nasty, smelly, undrinkable. And he looked at the good wine versus the bad wine under the microscope and found that there were certain molecules, at the time called endomolecules, we now call bacteria or yeasts, that were present in one or the other. The yeasts were present in the good batches. The bacteria were present in the bad batches. And if that wasn't good enough, he came up with a process to kill those bacteria. Who wants to name that process? Pasteurization, very good. So figured out that you could heat these liquids enough to kill the bacteria but not disrupt the fermentation process, and saved the French wine industry. He did a similar thing with the silk industry. He was also able to do something that had been dogging science for a long time, which is come to a definitive yes or no on whether or not life spontaneously generates. The old idea was, oh, you got a pile of hay, well, that hay turns into mice. Why? Well, if you have a pile of hay, eventually you see mice. Oh, there's some meat. Well, the meat makes flies. Why? Well, if there's meat, sooner or later there's going to be flies on it. He was able to show that if you actually kept dust and other contaminants from touching these things, they would never rot, per se. And that you never got life from these things unless you allowed them to actually contact the external environment. So he did a lot of really good things. We'll come back to Pasteur another time as well. Big thing to note is that the microscope figured very prominently in his ability to make these discoveries. I'm going to back up real quick. The other thing he was really good at, self-promotion. As bad as Ignaz Semmelweis was at promoting his good idea, Pasteur was incredibly persuasive and incredibly, we can call it arrogant, but if you're arrogant and right, then you got something going for you. But he would really push his ideas forward because they were massive advances. And he made a lot of people unhappy in the process, but he was able to communicate so effectively that his views won out. And thankfully, his views were more correct than not. So now we have the idea that bacteria, these little tiny organisms, can cause disease. Robert Koch was able to show that it's not just any of these little things, these little bacteria that can cause disease, but specific ones cause specific diseases. And the first disease he was able to tie to a specific animal, or animalcule at the time, was anthrax. So the anthrax bacillus was shown to only cause anthrax. It doesn't cause other diseases. You don't get anthrax from Clostridium bacteria. It has to be from that specific organism. And thereafter, many other diseases were figured out to be based around bacteria. Viral diseases took a lot longer because you can't see a virus under a light microscope. Viral diseases took a while for people to figure out what the cause of that was. So we're going to jump to another topic altogether now and talk about neurologic disease. What causes disease in our brain? Our brain is pretty well protected. Infection has a tough time getting to it. Trauma generally has a tough time getting to it, but occasionally it can, and occasionally that trauma doesn't kill us outright. In 1848, a guy named Phineas Gage was working on the railroad all the livelong day. And his job, he was a foreman, and he had a tamping rod. So a person ahead of him would drill a hole into the rock they were trying to blast to lay down the railway. Another person would come in, put some blasting powder in there. Another person would put some cotton in there, and he'd come along with a tamping rod and kind of tamp it down so that when the explosion happened, it was relatively contained, and so forth. The tamping rod had a spike on it, and the person ahead of him with the cotton missed a hole. And he put the tamping rod down, ignited the gunpowder, and the tamping rod shot through his jaw and out the top of his skull. That's actually his skull at the Harvard Museum of Medical History. Now, they call it the Harvard Museum of Medical History. It's a hallway. It's really cool. It's worth visiting, but it's a hallway in a quad building. So a little grandiose nomenclature there. But they have cool stuff. And essentially, amazingly, he not only survived the injury, he survived the possible post-injury infections that could have come around, but the damage done to his frontal lobe caused massive changes in his personality. Now, a lot of things you read about him say he was completely disabled, he was violent and unpredictable, a bit, but as time went by, he actually got better. He died eventually, fairly old age, but after being able to maintain work as a stagecoach driver in Argentina, he could do some work. But the person he'd been before was different from the person he was after. And this was the first evidence we had that the brain and specific regions of the brain control some of the things that we would otherwise say were kind of integral to our existence and our personality. So, in Europe, neurologists were able to look at how patients were progressing if they had neurologic disease, and then after a post-mortem, they could look and see where damage occurred in the brain. And the big names that either you know or you will know shortly, Broca and Wernicke. Broca described Broca's area based on one of his patients who had the inability to form sentences and speak clearly. And it was because a specific area of his brain had been damaged. Wernicke was able to actually find the counterpoint to that, an area that's a little further back. I couldn't find a copyright-cleared image of a Wernicke's area lesion, but it's just a little further back, but it causes receptive aphasia, the inability to understand language, yet make it fluently so long as the area called Broca's is still intact. So we're finding that specific neurologic areas have specific effects, and that countered the prevailing idea at the time, which was that the brain was a vast network and it all intercommunicated and it wasn't localized in any way. It was all a big network. So what constitutes the brain? The cellular studies that were done by Ramon Cajal and Camille Golgi were able to set down that the neurons in the brain communicate with each other in a very sophisticated way, and tying that together with the regional activities of the brain could explain about how a lot of diseases and neurologic problems manifest. Cajal came up with a silver staining method that he used to draw areas of the brain, and Golgi, who named a ton of things anatomically, you're going to hear a lot of Golgi this and Golgi that, he was the one who took that method and really refined it to the point where he saw that the brain was not, in fact, a network of completely connected cells, like Cajal thought, but was actually made up of discrete neurons that had little tiny gaps between their neighbors, and those synapses separating them not only from their other neuron neighbors, but from their target tissues. So they shared the Nobel Prize for this discovery and their work on it. All right, so let's talk about America. We haven't really touched on America yet because there wasn't much to say. American medicine plugged along at pretty much the same pace as medicine throughout Europe, but a little bit behind. Philadelphia actually started to have a really solid medical program develop around the hospitals there. And this guy, who you may have seen, it's a famous picture called the Gross Clinic. His name's Samuel Gross. He started the first course of pathology in the US, although he did disregard the germ theory of disease. He thought it was completely bogus. But he did start teaching pathology, and medical education, medical research in the US was primed to really take off. But the problem was we had a civil war. Who's heard of that thing? Yeah, I figured. You can either raise your hand or just kind of snarkily exhale. The Civil War was not just massively expensive, massively damaging, massively disruptive to America. It set us back at least 20 years. So all that medical progress that was primed to be made just didn't happen. The US became a medical backwater for quite a long time. And the thing that we had were called proprietary schools. There was no regulation at all. I could go found my own medical school, just put out a shingle, and that was that. Practitioners took in medical students who hung out with them for a couple years, or maybe even a few months, and they were then going to go out and be doctors. There's no quality control, no sort of certification involved, and therefore medical practice in the US was incredibly risky. The people who wanted to do good, solid practice went to Europe and trained in the German, the French, the Austrian hospitals. So US medicine, not so hot. So what happened? The Johns Hopkins Hospital and Medical School and College opened up in Baltimore. Johns Hopkins was a philanthropist who left his money, based around railroad stocks, for the founding of these schools. The problem was, by the time the medical school was ready to be founded, those stocks had lost a lot of their worth, and they didn't have enough money there to actually cover the cost of the medical school. The wives and daughters of people on the board said, we will go around the country and raise money, but if we do this, there's a few things you're going to do with this medical school. And these were, let me preface, these were outrageous, ridiculous demands. Had to be postgraduate. You actually had to have a college degree before you went to med school. Sound familiar? Students were expected to read English, French, and German. Okay, we don't make you do that. I hear you guys bitch and moan about the physics prereq enough. Okay, we don't make you do this. The school had to be associated with a teaching hospital. There actually had to be a hospital there where students could shadow physicians and actually learn on the wards. The medical faculty were expected to work at the school and the hospital and not have outside clinic to distract them from their teaching duties. And women were to be admitted on the same basis as men. Which of these was the sticking point? The last one. The board really didn't want to do that. They kept on hemming and hawing, wouldn't go for it, but eventually they had no other option. They said, okay, fine, we'll admit women too. And the fundraising was done, and it worked, and Johns Hopkins opened in 1893. Now, I underline 1893 for a specific reason. Johns Hopkins, legitimately, is considered to be the start of high-caliber education in the United States, but also the inclusion of women in medical education. However, in 1892, still opened the Kirksville School, and without a whole lot of parading around, included women on an equal basis as men, and the curriculum at the time was very much focused on the anatomical sciences. So it was a legitimately progressive school based around good science, admitting women on the same basis as men 1 year before Hopkins. But you don't hear about that because Hopkins is famous. And legitimately so. Hopkins, they did a lot of cool things. They found, as their founding faculty, 4 of the brightest lights in medical education, people whose names have really become just incredibly well known in medical practice and education. William Welch was the first pathologist and histologist there. He discovered Clostridium perfringens, which was really named after him, cause of gas gangrene. But he also brought in a lot of faculty who filled specific niches there. The first OBGYN surgeon with a specific professorial title in that, the head of surgery there, the head of medicine, William Osler. A lot of famous names came in, and he trained multiple Nobel Prize winners and oversaw the operations of the school. He could have done a lot more scientifically if he hadn't taken on such an administrative role at the school. And you can debate which one had the more lasting effect, his bringing in good people or his own practical experimental work in the lab. Now, in 1910, the Carnegie Foundation decided American medical education was just terrible and it needed to be reformed. And they enlisted a guy named Abraham Flexner, to do the work on this. And he looked at the medical schools in the US and made recommendations for how changes were to be made. And he said, well, we need to follow the Hopkins model. If you don't follow the Hopkins model, you should be shut down. Now, his name's Abraham Flexner. One of the faculty at Hopkins was Simon Flexner, his brother. So these days, massive conflict of interest. Back then, nobody cared. So at this point, the Rockefeller Foundation then said, we'll put up the money for schools to adopt the Hopkins model, and if they don't, the government should shut them down. So as a result of the Flexner report, medical education became more uniform, more quality controlled. Basic science, laboratory teaching, and hospital teaching became standard practice, and it got a lot harder for proprietary schools and low caliber medical schools to stick around. The AMA became the dominant voice in American medicine. So that's one thing that started happening that helped them shut down competitors like osteopathic physicians, midwives, and others. The MD schools cut in half. DO schools not quite cut in half, but you're dealing with a much smaller start. And it's unclear if there were 6 left afterwards due to some closing down, some merging. But as a result of the AMA becoming more vocal, the funding available for MD schools outstripped the funding available for DO schools, which is why DO research has really had a tough time establishing itself on the same level. It's getting better, but still hard work. And the DO schools remained ineligible, not just lower, but ineligible for federal funding until the 60s. So, we're going to now rocket through some of the more recent events. And they really are kind of tied to the theme we've had earlier today of medicine moving from the whole body to organs, to tissues, to cells, and now we get into the subcellular realm. In about 15 years, the foundational events that made modern molecular biology all happened. In 1940, we found out that protein structure and genes were related. Nobody quite knew what genes were, but they knew there was a heritable connection to how proteins were formed, and they're passing on to children of parents. In 1944, it was shown that DNA was linked with that. Thereafter, using borrowed or stolen, depending on which version of the event you're according, X-ray diffraction data from Rosalind Franklin, then Watson and Crick were able to describe the three-dimensional structure of DNA and how it actually operated as a heritable molecule. And then thereafter, we got how DNA and RNA and proteins are connected. So all of this happened within about a 15-year span. And the outcome is that then we had a new place to locate disease. We had genetic diseases now. And in 1989, the first disease with a genetic basis was unambiguously shown to be cystic fibrosis. It's a genetic disease causing a receptor mutation that made the mucus in the airways very sticky and hard to clear. And molecular biology continues on unabated. We've got CRISPR now. We've got a huge number of potential tools being applied that can radically change the way we diagnose and treat disease. So more on that as time goes by. All right, that's it for today. Next talk is going to be about how we actually treat disease. Now that we know how people thought disease came about, what are we going to do about it? And I guarantee all the solutions that will be here will be both clever and horrifying in alternating terms. Thanks again.